Right, finally we arrived at here, this portion of the video, Introduction to Elliptic Curves. First, we're going to focus on the binary operation. Just recalling the binary operation in this conic section that we discussed in an earlier video. The first thing we're going to do is to bring out this nice property that is known to the elliptic curves. To make an analogy, I'm going to consider these conic sections, consider over a finite field, Fp, and then P is a prime number. Doesn't have to be, but it could be powers and prime numbers, but simple enough. So we're going to consider this conic sections over finite field. So you go through all the pairs of modulo P and see which ones satisfy these equations. So here's a theorem, and this is actually something we did in our number theory class recently, and we actually use a SAGE to go and actually figure out a number of solutions over this finite field of this type, and that there's a nice observation could be made from that, and it is relying on the following theorem. Whether or not these are square in Fp, it means a quadratic residue or not, there is a solution. P, there's always a solution to that. Not only just a solution, there is actually a solution. So if you do that operation, now it's defined. If you think about that operation, I forgot to mention in here that we have this binary operation, something like, right, I think this is what the operation was. If you have two solutions, xy and zw, then we can create these two solutions. It came from the factorization and then the complex numbers and everything. But when we prove actually that these two things like this, if we generate new coordinate, the fact that they satisfied this equation again is a very straightforward algebraic check. Therefore, we have the same field arithmetic in here. So this law of a binary operation will still work in here, and that's the main point I have to point it out, and which I didn't write down here. So go back to this theorem. It says there is a single solution. So under this binary operation, if you just keep repeating operate on itself, and it's going to reach all the points that it's in this set in here. So it looks a lot like primitive roots. Mod B, which is usually introduced in an elementary number theory course, that in fact the way this was proved is exactly using this fact. But it's quite amusing that it looks like a lot more complicated arithmetic you go through, and the same phenomenon happens, right? So let's focus on this factor, and we're going to show you the proof, which is fairly simple. That's why we're showing it here. There is a single solution in here. If you repeat it to itself, this operation, it will reach all the solutions that is satisfying this equation over the finite field. So that's nice theorem. So single generator, maybe you can call that. So we're showing you the proof because it's fairly simple. I guess the proof is only simple when you understand this type of field extensions, and although most of the typical elementary number theory course will not introduce the field extension over a finite field, but which something we did in our course, so we are using this idea. Well, you have to think about just how you extended. If this is uncomfortable, think about the situation, how we went from a real number to the complex number. We just throw in imaginary number that no one actually can see. So that's the same thing. So square root of 2, square root of d, if that doesn't exist, d is not a quadratic residue mod p. Think about imaginary number whose square is d. Then you throw into the system. So that's the field in here. So that's a field extension. And the notation, adding p to itself n times will be denoted like this. This is standard notation. Multiplication by n, that's what it says. And secondly, we're going to kind of separate the, extract the information. So if you have a rational solution, here x comma y, then we can associate this one with that one of the factor, right, x plus y root d. And here in the finite field, there's no notion of positive and negative, so it's just going to be 1 of the square root of d, and d, itself is not positive or negative, doesn't matter. And now, of course, we use a lot of commutative diagrams. So here's the power of a commutative diagram again. So let me explain. This is the entire solution over this finite field, and we're associating each of this solution x comma y with this number x plus y times root d. That's a member in this extended finite field. So this is actually, if you think about it, it's really one-to-one. Each of them uniquely correspond to each other one-to-one. So it's the same information represented in a slightly different way. So what we're doing here is operation is that we are going through that complicated arithmetic operation n times, whatever that n is, and then we guarantee to land in that solution again. That was the magic. And if you think about the same operation over here, if you think about how the operation was defined, how did we go from here to more complicated operation like this, where there's a 2 times adding p to itself, and that's going to map to in here. We went through many times. You think about that idea, how did we get from here to there? What we really did is we actually raised that number, if I call that w, to the nth power. If it is a second, it's going to be second power in here. So let me raise that. If you really raise that to the second power, and we realize it is exactly in the same form and so on that we looked at. So multiplication by n in here in this complicated coordinate formula is really coming from just the nth power on this field. That's all that it was in this kind of disguised form. So what do we know about nth power of a finite field? Although we proved only the primitive root theorem for finite field, not for field extension of the finite field. If you look at our theorem, it uses nothing but the fact that this thing is a field. Therefore, that counting lemma, and all that we did in our class naturally extends to all the finite fields, not just the finite field with the p elements. So I'd like to claim it here. K star is a primitive. There is a one single element g, such that if you consider all that powers of g, it's going to eventually repeat. And not only is it repeating, it actually goes through all the elements in K star. So if this is going through all the K star, and because of this bijection and this point that we started with, whatever that corresponded here, the primitive roots, that we figured it out, and as we multiply it by n, it's going to go through all the points. So I wrote it down here. The existence of a primitive roots of this field extension k, and that means if you consider all the powers in here for a fixed element, that goes through everything. So that explains there's one single point that corresponds to this primitive roots for this finite field that goes through all the points. So let me go back and show you the statement that there is a single solution. If you operate to itself many times, eventually it's going to go through all the points in here. So that was nicely explained using the primitive root. And if you think about it, the very nature of the solution set is really just the arithmetic on this finite field extension. That's another conclusion you can draw. So in other words, this wasn't really complicated curve. So we explain nicely with a K star. Remember that was actually over the finite field, but if you think about over the rationals, I forgot to write in here an over the rational numbers, not finite field solution. If you look at the rational solution, there will not be a single subset of finitely many solutions that will generate entire solution under this operation. If you look at all the rational solutions, this will never happen. But it happened that over the finite field, there is a single solution. As we repeat this operation, it generated everything. But over the rational, it doesn't. One way to look at that is that if you go back to this binary operation in here, you can see if you have some of the solutions, this operation itself does not involve any division. So if these one have a common denominator, something, and this new solution will have the same common denominator squared. So you don't introduce any extra prime factors into that, but you will find lots of other solutions that with a different prime factors in here. So if you have some collection of points, as long as it's finite, there's always a common denominator, and you will never see any other prime factors appearing that doesn't divide the common denominator in here. But there are many solutions with a denominator supported by different primes, they say. Alright, so this is important thing to point out. So I forgot to mention this, so I'm adding in here. I'd like to say if you enter next level, for example, we started this whole discussion with this simple equation coming from Pythagorean theorem, then what could be the next level? I think is a natural way to go. The next level is x cubed plus y cubed equals 1. Then, and you can ask this question, is there a way to pull out, maybe by looking at the factorization of left-hand side, pull out some nice operation on here such that we have the same phenomenon. We have 2 points and we can generate third point. One thing we can't, one of the ingredients we don't have in it here, and after you factor, and you will have 3 factorizations like this, and it's equal to 1, but if you raise that to the nth power, for example, or if you have a different solution, if you just multiply it side by side like that, you don't keep this form itself again. Alright? So that's the one thing that we don't have. So why don't I just, since I mentioned this one, why don't I write down the factorization here? So the factorization actually looks like this. It's a very well-known fact that this zeta here is a primitive third root of unity in the complex plane, and you can write down explicitly what the real and imaginary parts are. What's important is the structure like this. All right. So, and if you use a different the same technique, we want to, for example, raise to the nth power. Then, if you raise to the nth power, if you raise that to the nth power, if you raise that to the nth power, because the zeta actually satisfied a smaller degree equation, namely this one. This is the defining so-called minimal polynomial for the primitive third root of unity. Because of that, all the squares can be written in terms of linear, in terms of zeta. And this one, same, this is wrong, so I'm going to change that to 2. And the same thing, the zeta squared can be written in terms of zeta plus 1 like that, and after you raise it, you can always rewrite into zeta plus 1. So I'd like to claim that if you raise that to nth power, if you raise that to nth power, if you raise that to nth power, they're all going back to this exactly the same form. It's going to be written like this. Sum of 2 rational numbers, you can write it, and you can go back to this form. You can go back to that form after you raise to nth power. However, this x and y appearing in here may not be exactly x and y you're getting in here, and that's actually exactly what happened. So if you actually raise to the second power and try to rewrite it using this identity, and you will notice that this x and y that you're seeing in here are not exactly the same. There's no way to split this number into two parts to match these two things. But it turns out when we looked at the second idea, the parameterization idea, there's a way to pull up some sort of operation from there. Because this has a degree increase like this, one more, there's room to play with that when you're sweeping a line.